We'll start with the lecture on XRD basics, the second part of this. So this would be altogether our lecture 4, but XRD basics will continue with this. As I mentioned in my last class that XRD plays a very important role whenever you are doing any kind of characterization technique. So the diffraction peaks that we actually see in an XRD uh, result is basically nothing but associated with the plane of the atoms. So typically a XRD result will look something like this, okay, and if we look into the labeling or indexing of these peaks, we label it with something like this, which are three numerical values, and they are basically called as the Miller indices. So Miller indices concept is already clear to you from your solid state physics, and this basically identifies the different planes of the atoms. So if I have a Miller indices of 110, it means that this includes all the atoms that are included in that particular plane. So if we have more and more atoms in that particular plane, the diffraction peak is going to be observed very clearly. So this observed diffraction peak that we are actually talking about can be related to the plane of the atoms, and it will basically assist in analyzing the atomic structure or microstructure of the sample. So if we are able to know what is the position of the Miller indices at a particular 2 theta angle, please remember this, the x-axis is 2 theta, so these are all angles. So at a particular angle, if we are able to find out what is the Miller indices, we can actually comment a lot about the atomic structure, which we are going to see in the near future. So whenever you are doing any kind of characterization and you have an XRD analysis, it's very important that you index it correctly, and this is what is there. So this parallel planes of atoms which intersects the unit cell defines the direction and distances in the crystal. Okay, so if we have a plane of atoms, so you can see here there are three planes which are shown here. So this is one plane, this is the second plane, and this is the third plane. All three of them will have the same set of Miller indices. Now this Miller indices is basically taken in the reciprocal space. All of you might remember reciprocal space from again solid state physics. Reciprocal space gives us a better picture because we can actually consider more number of atoms there. Okay, so what we have here is these three will actually have the same Miller indices. So this is nothing but the 200 plane of the sodium chloride crystal. So this is basically a 3D animation, and this whether you go into this plane one, the first plane, the second plane, or the third plane, all of them will have the same Miller indices of 200, and the atomic arrangement which is shown here is nothing but for sodium crystal. Okay, so even if we consider something like the sodium crystal, and if you are considering the 220 plane, okay, the 220 plane would be this. So this will be first plane, this would be the second plane, this will be the third plane, and so on. So if other planes are there on top of that, all of them will belong to 220 planes. So that means this value of 220 will represent all the set of planes which are parallel to each other. So this crystallographic direction, which is HKL, is a vector normal to HKL. So if you consider the crystallographic direction, this will be basically a vector which is normal to this. Okay, so this is a vector, this is the crystallographic direction, or this vector, this is also the crystallographic direction. Now this vector is basically represented by a term which is, we have the DHKL. The DHKL vector, which is basically originating to the plane HKL, this is basically nothing but normal to all the set of planes that we have. The vector DHKL is used in Bragg's law, and if you remember with the Bragg's law, we are going to look into it into the next slide. We are not going to really derive Bragg's law, but we are going to just have a look into it. So Bragg's law is usually given as lambda is equal to 2 times DHKL sine of theta. Now lambda is the wavelength which is actually known. Okay, so now lambda is known to you, and 2d DHKL is nothing but a vector which is perpendicular to HKL plane. Okay, HKL plane, that is the Miller indices, and theta is that same theta that we have, which is nothing but the diffraction angle that we have. So what we need to note here is that the position of the diffraction peaks are determined by the distance between the parallel planes of atoms. So if we have one plane here, so let's say this is the second plane, and this is the, let's say, the another plane which we have. This DHKL will actually represent, this is the second plane that we have, this DHKL, that means this D110 will represent the distance between these two planes. Now this is also characterized or calculated from the XRD data. So what does Bragg's law exactly do? The Bragg's law actually calculates the angle where the constructive interference of X-rays scattered by parallel plane of atom will produce a diffraction peak. So the angle, so that means from Bragg's law we can actually definitely find out this angle theta, where exactly the diffraction peaks will the interference will, constructive interference rather, will take place, and we will get a diffraction peak. Now in most diffractometers the X-ray wavelength is fixed. We are going to look into this factor. Most of the times the X-ray source that is being used is nothing but copper, okay, and you have to know obviously how X-rays are produced in any atom. Now the family of plane will produce a diffraction peak only at a specific angle 2 theta, okay. So 2 theta, why it is 2 theta and so on, we are going to look into in our future classes, but right now let's just consider this, that the diffraction peak will be produced only at a specific angle 2 theta. Now what is DHKL again? So DHKL is nothing but the vector drawn from the origin of the unit cell intersecting the crystallographic plane HKL at 90 degree. So if you look into this, this intersects, this is DHKL, and this intersects here in the plane at 90 degree, okay. So this is intersecting at 90 degree, and DHKL is a vector magnitude, basically it's a value, okay, and is the distance between the parallel plane of atoms. So if you are considering D100, this will actually give you the distance between the two planes. So this is obviously a geometric function, and it will actually depend on the size and shape of the unit cell, okay. So what atomic arrangement we are considering, that will actually define what is the DHKL value, or in other words we can say for different atomic arrangements we have got different DHKL value, okay. Now what are the factors on which the intensity of the diffraction peak depends? Now we know that the diffraction peak are occurring because of the interference pattern, but the interference pattern may not be very perfect, and we might not get a very intense peak all the time, because there are other factors which also depends which decides the intensity of the diffraction peak. So this intensity of the diffraction peak is directly proportional to the square of a factor FHKL, which is basically called the structure factor, okay. So what is the structure factor? The structure factor mathematically can be written in this way, okay, where there is a factor Nj, when there is a factor Fj, and there are Xj, Yj and Zj, okay, and of course the HKL. So the only term that we have already learned is nothing but HKL, the Miller indices, okay, and then let's see what are the other terms here. So FHKL, which is nothing but the structure factor, which will sum the result of scattering from all the atom in a unit cell in a diffraction peak from the HKL plane of the atoms, okay. So it will sum up all the HKL planes here, okay, and then what is the diffraction peak that is coming out, at what angle that they are coming out will decide what kind of constructive interference we are going to get, okay. So the amplitude of this scattered light is determined by where the atoms are on the atomic plane. Obviously if they are very well aligned and one below the other, the positions, then obviously it's going to get a very intense diffraction peak, but then what is their exact position will be actually dependent on the coordinates on which the atoms are placed. So these are all nothing but fractional coordinates, okay. We are going to see where we are how we are actually understanding fractional coordinates later, but right now we can say these coordinates will define the position of these atoms, and of course where the atoms are on the atomic plane, okay. Now the scattering factor Fj, now we have got one more factor which is called Fj here, okay, and this will actually quantify the efficiency of the X-ray scattering at an angle by a group of electrons in each atom. This Fj determines how efficient the scattering is. Now you can understand this because scattering sometimes doesn't happen, the X-rays can directly pass through the atom. So how efficiently they are scattered will depend on this factor, and this factor is equal to the number of electrons that are present, okay, but that is also at an angle 0 degree, okay, because if that X-ray which is present is not at an angle 0 degree and it deviates the value from of theta, that means the scattering will actually keep on changing, okay. So scattering will keep on changing. So we need to have the atoms arranged at 0 degree theta, so that we can have maximum intense diffraction peaks, okay. Once they deviate from this value of 0 degree, there is going to be the intensity of this diffraction peak are going to drop, okay. And then finally we have got a factor which is called Nj. Now Nj is the fraction of every equivalent position that is occupied by the atom J. So the equivalent position that is being occupied by the atom J is given by something which we call as the Nj, okay. So these are some of the factors on which the scattering on which the diffraction peak depends, and this FHKL is called the structure factor. A question might be, what is structure factor, or what are the factors on which the structure factor depends? So might be a 2 marks question for this, okay. But if we just go further into Bragg's law, and what does it do? It basically provides a simplistic model to understand what are the conditions required for diffraction. So we have got lambda is equal to 2 DHKL sin theta, but you need to remember that the diffraction peak also depends on the structure factor. But for having a diffraction, one of the simplest approach is to understand what is Bragg's law in each of the terms, okay. So if we consider a parallel set of atoms, so if you consider this here, so this is one set of atoms, this is once again, this is the third. This is not the real picture, this is nothing but an approximation, and we are putting up the image there, okay. Previously the 3D diagram that has been generated with some computer aided software, that is actually a real more closer to the real picture. Here we are just representing the planes. So if you have got the parallel planes 1, 2 and 3, and then each of them are separated by a distance DHKL, okay. So DHKL is nothing but the separation between the planes, and there will be a constructive interference which will happen on when the Bragg's law is satisfied. So Bragg's law is lambda is equal to 2d sin theta. When this law is satisfied, we are going to get something which we call as the constructive interference. But we need to remember that this value of lambda is fixed because we are using an X-ray source which is already known to us. For this we can use actually a copper source mostly, where okay, anyway we are going to just look into that in the next slide, okay. The family of the plane will basically produce a diffraction peak only at a specific angle 2 theta. Now this concept of 2 theta, I think you have to understand when we actually derive the Bragg's law, okay. But this is the theta or the angle at which the ray of X-ray is actually diffracted. So if this is theta and there are parallel plane, this will also be theta, this will also be theta, and so on. So if we have got more and more parallel planes and more diffractions are taking place from there, and then it is going to interfere constructively, and as a result of which we are going to get the interference pattern which is good to determine the planes, okay. So before we proceed further, we need to know what are the common sources and the X-ray wavelength that we are talking about, okay. So what are the factors by which we can actually determine the X-ray wave, or on which the X-ray wavelength depends? Well, one of the major part is nothing but what kind of element you are using to generate X-ray. So in general, you can use a chromium source, an iron source, a copper source, or a molybdenum source, out of which most important is copper, okay. Copper is mostly used, okay, because it produces a very intense peak. So a brighter incident beam of X-ray is produced from a copper tube, okay, than from a molybdenum tube at the same power level. So if you are using some kind of power in from copper, we are going to get a brighter X-ray compared to something like a molybdenum tube. So if we consider a very small crystal of strongly absorbing material, okay, strongly absorbing material, it will often yield better diffracted intensities, okay, from copper radiation than from the molybdenum radiation. So that means our final aim is actually to get the diffraction pattern. So if you want a very good intense peaks and intense diffraction pattern, it's always better to use a copper source, because a copper source will have the small crystals will strongly absorb the X-rays from the copper source and generate a good pattern, okay. Occasionally other type of target materials are also used, for example chromium, iron, tungsten or silver, but they are only chosen for specialized diffraction experiments. So in your questions which might arise, that is copper the only source, the answer is definitely no. Copper, apart from copper we can use other sources also. In fact after copper, molybdenum is also one of the popular sources. So what is the thing that we know from the copper source? What we know is basically nothing but the wavelength of the X-ray. Okay, so if you consider a copper, okay, the atomic number or the Z value, okay, so the number of protons that we have here basically is nothing but 29. Okay, so you should know more about the copper, and there are some X-ray lines which are generated, which you are going to see into the next slide. And for copper the wavelength is 1.54051 for K alpha line, and for K alpha 2 line we have got 1.54433, and that average is 1.54178. So most of the times for any practical purpose the wavelength that is being used is nothing but 1.54 for copper. Okay, so if we use this wavelength in the Bragg's law, we already know what is the value of lambda, and from the graph we can find out what is the value of theta, and from there we can find out what is the value of HKL that can be determined. Okay, the generation of X-rays. How do we actually generate X-rays now? So before we go to why copper is used or how copper is used and so on, we need to know some terms which are nothing but the alpha lines here. Okay, and we also need to know that why we use copper and how X-rays are actually generated. So before we go to the generation of X-rays, let's just look into some basic points. So we have got basically an atoms, let's say, okay, and these atoms are externally excited by high energy short wavelength radiation. Please remember, these short wavelength radiation can even be X-rays, okay, which are sufficient energy, so they can actually generate some more X-rays, because what happens is dislodges the electron, because of which some X-rays are getting generated, which we are going to see in the next slide. Now the electrons basically are in the inner atomic shell. Okay, so if we consider our X-ray system, that means we have got the nucleus and we have got the shells outside it. Okay, and then there are some electrons which are present and revolving around this. So these electrons basically are getting knocked out by from some rays which are coming in, and they are getting dislodged. Okay, and they are basically replaced by high energy electrons from the outer shell. Now in order to maintain the conservation of energy, some kind of radiation must come out of it, which is nothing but the X-rays. Now this high energy electron must release energy to fill the lower energy vacancies within the atom. Okay, now this energy is emitted as photon. Now if we are talking about any kind of electromagnetic wave, X-ray is also an electromagnetic wave, so they are basically emitted as photons, which can so the wavelength characteristics is the difference between the initial and the final energy state of the electron or the outer and inner shell electrons. Okay, so let's go to the next slide to understand this particular point. Okay, so if you go into the next slide and look into a diagram, we basically have got an electron here, and then we have got some kind of radiation which is coming. It might be anything, it might be high energy radiation, so it might be, let's say, an X-ray photon. Now this X-ray photon, what will happen, it will actually eject an electron. The electron will come out of the system. Now there is a vacancy which is created here, and an electron from a higher energy level will come and fill this up. Now as the electron comes from an higher energy level to a lower energy level, some kind of radiation will go out, which is nothing but the X-ray again, which we are talking about. Okay, now this can be the beta lines or the alpha lines. Now if you look into the cell structure, we have got the electrons in the K, L, M and so on, but mostly when we are talking about generation of X-ray, we can consider only K, L, M and N shells. Okay, if you look into the energy level diagram, and before going there, what you can say is the K shell, which is represented in this particular diagram, it's the lowest energy electron shell and the innermost shell, or it's closest to the nucleus in general. Okay, now these lines that we get are nothing but the characteristic energy of the emitted photon. So what are these lines that we are talking about? These lines are nothing but the energy of the emitted photon or the or the X-rays that are coming out, and since we know the energy, we can definitely find out what is the wavelength. Okay, so it's very simple because we already know the relation E is equal to hc divided by lambda. So if we know the energy, we can find out what is the wavelength associated with it. Okay, So what happens is, if there is a electron which is knocked out from the K shell, and from the K shell, and then we have got a electron from a higher energy level, let's say m, going and filling up the K shell. Okay, there will be the radiation coming out, and there is also a chance that there will be some kind of electron which will actually go from the L shell to the K shell. So if we have got from the L shell to the K shell, that is from the immediate next energy level, then we basically call them as the alpha lines or the K alpha line. Okay, and if it goes from M shell to the K shell, we basically call as the K beta line. Why K? Because the final level at which the electron goes and sits is nothing but the K shell, and alpha because it comes from L level, and beta because it comes from the level M. Okay, but there might be another transition which is possible, that is from M to L, because some vacancy is also created in L because the electron in L has gone to K. These are called the L alpha line, and from N to M basically are called the L beta line. So this is basically called K excitation, which is more important for X-ray, and this is called the L excitation, which is not very relevant. Okay, but now we need to understand what kind of X-ray do we use for XRD analysis. Well, it's mostly the alpha lines that we are talking about and not the beta lines, for the simple reason that the alpha line has got a higher counting rate compared to the beta lines. So what happens is, the electrons from the next higher level, energy level, substitute into the low energy level with greater frequency than those from energy shells further away. So this will replace from L to K with greater frequency compared to an electron replacing from M to K. Okay. So that's why we are using the K alpha line. Okay, but after that we need to know what are alpha 1 line and alpha 2 line. Now if you look into the shell model, these energy levels can be split up. Okay, because of Pauli exclusion principle, and if there are heavier atoms, more number of electron needs to be accumulated. So if you consider the L line, we are basically going to, or the L shell, we are going to have two levels here which are very close to each other. So if that is from a level 2 to the K shell, okay, from level 2 to K shell, we basically have got something which is called the alpha 2 line. Okay, this is alpha 2. Okay, so we have got an alpha 2 line. On the other hand, if we have something like level from the third level to the K shell, we are basically having something which is called the alpha 1 line. Okay, so these are alpha 2 and alpha 1 line. Both are very close to each other, and sometimes it becomes a bit difficult to resolve, but in general, if we are going to do this analysis, what we can do is, we can take an average of these two which are actually very close to each other. So for all practical purposes, if we consider the wavelength of any one of the alpha lines, that should be more than enough to do our practical calculations. Okay, so this is what is meant by the alpha 1 and the alpha 2 line. Okay, so that's all for today. In the next class, we are going to continue with the more practical applications of XRD and the more of the technical terms there. Thank you.